All right, thank you very much. Thanks for having me today. It's really a pleasure to be here with you today. So today I'm gonna be talking about something that we don't hear often, that you actually don't need GPUs to run your AI workloads, and I'm gonna here to prove it, right? So my name is Melendez. I work for AWS as a specialist compute SA, focused primarily on helping customers on making the most of EC2, Spot, Graviton, AMD, Intel, you name it. Right, so as I was saying before, some AI workloads don't need GPUs, and I'm going to show you why and prove it live at the end of the session. When I say about SLMs or small language models, I mean models between 1 and 8 or 10 billion parameters that you can run effectively on CPUs. We have many customers running this on CPUs as well. So imagine this, what happens when you paste something, a Kubernetes config, into a big LLM? Your favorite tool, doesn't matter which one, at some point they will lie to you, as we were seeing before in the previous session. So imagine that you have a notebook manifest of Carpenter like this, and you ask, what does mean values do? Is my config correct? I saw this and I don't know what that means. So the LLM is gonna say, like, hey, but mean values is not a standard field in Carpenter's requirement. This is wrong. What mean values actually does is that ensures the type of diversity that you have for Spot instances is gonna be met. And it's a way for you to guarantee the number of instance types that you can have on the call to EC2 API fleet, for example, right? So you can see that it was a well-formatted answer that might look correct, but actually that was not correct, and that's the dangerous part. And you can argue that to me, well, maybe the prompt was not well-crafted, and you need to think about how to craft it. Yeah, that's right, but at some point, when you start interacting with your LLMs, at some point, you might just mess things up, and you will forget at some point that is it true or is it not true, right? So these things will happen. And this is not something against frontier models. You might need them, but you might not need them. And there are certain tasks, there are certain attributes that will make particular SLMs very attractive for some users, right? And the reason for this is essentially LLMs are not trained or might not be trained in your expertise, in your domain expertise. And depending on how they've trained and the data that they have, they might be accurate, they might not be. And I use this example because I'm passionate about Kubernetes and autoscaling and so on and so forth. But might be something else, might be something that the LLM doesn't know about it. So how can we cope with this? So it's not me the only one saying this. Salesforce actually proved this a few years ago, that an 8B model was able to beat a GPT-4. It doesn't matter if it will be another model, doesn't really matter, but what matters here is that a small language model specialized in something was able to beat a big brain on certain tasks. That means that specialization beats sizes. You can have a really small model that is expert on something, and it's gonna help you to basically make the CPU story into AI workloads. NVIDIA actually published a paper last year saying that the future of agentic AI is leveraging on CPUs and small language models mainly. That was the premise of the paper, right? That the small language models are the future of agentic AI. Let me explain to you what does that mean, and at the end of the session, I'm gonna try to prove it with a demo that I built as well. And Andy Jassy, our CEO as well, says like agentic AI is becoming almost as big a CPU story as a GPU story. So you can see that the trend is going towards this, and you're gonna start seeing more and more adoption of CPUs into the AI ecosystem. Which workloads or which companies are already doing this? AI search companies, code editors, messaging platforms, food delivery, doing some fraud detection. Some of them are actually running models, maybe not generative AI models like we know them, but recursive models, classification models, ONNX formats that are already running on CPUs, and they might not need a GPU for doing that. This is not only one company doing this. I've heard this more and more often with customers that I talk to every day. So what does that look like in the API and the AI pipeline workloads that run on CPU? So at the center, you might have an LLM, but surrounding that LLM, you might have other parts of the ecosystem that might be, again, good options for running on CPUs. That will be embeddings for a rack system that you would like to do, classification, fine ranking, batch scoring, so on and so forth, right? So this session is not about saying, like, hey, GPUs are costly, are bad, don't go for them, don't go with LLMs. Actually, they are awesome. They are really awesome if you can take advantage of that. But my premise is that depending on your workload and your SLAs and your needs, you might actually not need that. So CPU and GPU are actually working together, as you can see. And the premise of this is that you have to use GPUs what they're good for, and perhaps just use CPUs what they're good for as well, right? So there are alternatives for this as well. To give you a little bit more of perspective, why my premise of saying like CPUs for AI workloads, especially in a Kubernetes ecosystem, we already have the primitives there that you already know. You don't have to think about device plugins, no GPU operators. The good thing is that if you are able to quantize or make the model smaller, you can actually feed it into a CPU memory, and it's gonna work. It's gonna work. I'm not saying that it's gonna beat in throughput and latency a GPU, but it's gonna work depending, again, on your SLAs and the task that you define an SLM to perform. The next thing is that multi-architecture flexibility that you can have with CPU instances. You can run ARM with Graviton, you can run AMD, Intel. You have a lot of options to run your workloads on CPUs as well. And I was saying before, simplicity in operations, you don't have to think about it. How to deploy your workloads, it will be like any other CPU-based workload that you're already deploying nowadays. All right, so the models that I mentioned before, classification, re-ranking, some of them are already running or running on CPUs, but there are certain tasks that you might want to start running on CPUs, and you better be expert on that, or you basically fine-tune your model to be an expert on a certain domain. So the pattern that I'm going to talk about is pretty simple, but it's very powerful, and it's basically the base of the demo that I'm going to show you today. So you can think about when you say, like, hey, where can I run SLMs, or what can I do for SLMs? If you think about high repetition tasks that you have, very common questions during the day, of course, you can argue that you can have prompt caching, any technique that you might have, but again, you're basically using the LLM for a task that it might be not suited for, right? When you have structure output in a multi-agentic agent system, you might have other agents that you would like to return structure output, and those workloads as well, or agents where you would like to have a low semantic variation. For that, use SLMs. So imagine that you work with an LLM. We can come and bring back all those patterns that we've been working for many years now, and you can start thinking about of these patterns, of these sections on your LLM or your AI pipeline, which are the parts that could be an SLM a good fit for. And then you basically start replacing parts of it, implementing the strangle pattern as I'm showing you here in the picture. So a pattern that works is a tier architecture. Imagine that you have, if we translate the query that I showed you before, you have the query there, and you have a small language model doing a triage, saying that, okay, I got this, I execute the prompt, or I process the prompt in a prefill, and I say, like, okay, this is basically my area of expertise, so I'm gonna go ahead and I'm gonna start and continue with the pipeline. Else is just basically noise, and it's not my responsibility to take it. Or if my routing is basically low confidence, it's gonna say, like, okay, this is actually a good call for an LLM, so I'm gonna fall back to an LLM. So rest assured that you have this architecture, this pattern, that can actually leverage the efficiency of running on CPUs, but can also fall back onto an LLM API, or if you're running GPUs as well, right? So what I did is I created a project that I called Slemify. It's open source. You can see the link at the end of the bottom of the screen. I'm gonna share the links later on. But basically, this is kind of like you can convert, or is how you can build an SLM with a CLI. You basically bring your raw data, leave it to kind of like the labels that you're gonna use, and the CLI is gonna use GPUs for training, for fine-tuning. It's gonna produce an SLM, and it's gonna deploy it or serve it in your cluster as well, so you can run some analysis as well, right? So I'm gonna show you how that works, but let me show you first how you can actually use it, right? So there are 3 stages, as I was saying before: the data stage, the training stage, and the service stage. If you look closer to these different stages, you're gonna notice that I'm actually not focusing only on CPUs. It's not only about CPUs, it's not only about GPUs, it's actually combining the whole ecosystem and knowing which type of compute works for you and in which stage, right? So for example, for data, I'm using LLM, or in this case Bedrock, to generate synthetic data. I'm running using GPUs for the training and serving on CPUs at the end for efficiency, right? So let's keep diving deep into this. So the output that you need to bring to Slamify is just a YAML. I'm not gonna go into all of these labels, but because I'm going to show you the project later on, you can actually just define the name of your model. You define what it's going to do, and then you define the labels, the model as a base that you're going to use to fine-tune it, et cetera, right? And then on the data stage, for example, what I did for the demo is actually a chatbot for a Kubernetes auto-scaling expert. I was able to get 75 emails or YAML examples or real queries that I constantly get from people asking me questions like, hey, I got this, but this LLM API gave me the answer. I just want to validate with an expert if this is true or not, right? So I got like 75 emails from this, and with generating synthetic data pairs, kind of like Q&A questions, basically, I was able to generate this data. I can validate each stage before proceeding to the next one, and I can go and fine-tune it later, right? So the better the data that you're gonna have, the better the model is gonna be. Here, there's no discussion about it. Data is gold in your AI agents as well, right? So next phase is gonna be the training phase, the fine-tuning phase, and what I'm doing here is just basically using a base model and fine-tune it. That means that I'm just gonna train small parts of the model. I want the model to keep its intelligence, but I want to teach it. It's like a kid, right? So I want you to keep that knowledge that you have already, but I'm gonna teach you something very specific for this. So I'm gonna teach you about these Q&As for the emails that I have as a source, and I want you to learn the pattern so that when something out of these 76 emails comes, you understand the pattern, right? So it will be very difficult to build a program or too many variances. So it's basically why we're doing, right? So in this case, I'm happy to go over the project. You can go, I built actually deep dives on each stage, even deeper than what I'm able to share in 30 minutes. But the output is that I was able to train this in a single GPU for 20 minutes, and it cost me 50 cents on spot. It's actually fault tolerant, so if I get a spot interruption, it can, based on the checkpoint, it can recover automatically. It's pretty awesome. So what it does is that the training, it's gonna generate the model on a GGUF format. It's basically a format that is gonna be able or to help you to run this in many different instance types as well. AMD, Intel, Graviton, as I was saying before, and the idea is that you quantize the model not because you wanted to create a model that is less intelligent. There are studies and there are tests that actually the accuracy of the model degrades just a little bit. Of course, you have to test it and make sure that it works for your workload. I mean, you have to be sure and you understand that models still are non-deterministic, right? So that's out of the equation. So I quantize it simply to make it efficient so that it fits into the memory and I can run more inference into this. Then the last stage is basically serving. I deploy it on CPU and I generate a report on this. So let me show you this. The total cost of all of the experiment of building this model was $30. Not by month, just by running this. So let me show you this. This is basically the project. It's called SLMify. It's actually fresh from the oven. I made it open source last Friday. And you can actually go and look at this and how to get started. I show you how to get started, give you a few examples, and the deep dives that I was telling you before. Each stage, I explained the technologies that I'm using, why I'm using those, and the reason of why those made sense. The last thing, you can actually connect it with your Cloud Code, Codex, Keto, or whatever you want, and you can actually connect this to this CLI, so it can guide you on finding out which part of your LLM or your AI pipeline are suitable for running LLMs. What I want to show you here is that the final result here is that it's going to build a report like this, where it's going to give you the accuracy. Of course, it's going to run some tests on your model, basically because you deploy it into your cluster. And without getting too much into the weeds, you can see here the comparison of a few questions that I did to the model and the confidence that it was able to give me. The SLM versus LLM, simply because I wanted to make sure that I know at least the answer that I get by running my SLM compared to an LLM. You can see that the LLM is more verbose. It's not structured at all. Of course, if you want to do it, you have to work on the prompt. And there are some graphs for the training and some metrics about that I use for the training. And this is the most interesting part, right? The capacity planning. So you can see here that at some point, if you're running very low request, you know what? Stay with your LLMs because you might not get advantage of it. You might be overcomplicated. But at some point, if you, for example, are getting 10,000 requests a day, then you might start to consider CPUs as well, right? So you can see here that at some point, GPUs actually go and tell you, hey, you know what? You're sending me too much traffic, so let's, the maths actually said that you may actually better to use GPUs as well. So this is basically what the reports are gonna produce. And I did the same for two models that I'm gonna explain to you later on the final demo, right? So to getting closer into the end, how do we run this into production? Once you have your SLM, how does that work? So what I've been testing and what I've seen with customers running is that we use Llama CPP as a runtime server for your model. It's the most mature at the day for running CPU workloads or using CPUs for AI MLs workloads, and BLM as well, but CPUs are not a first citizen, and I have a few customers that have been struggling on making this work on CPUs as well. I'm not saying that this is not gonna stop evolving here. You know that things change every week, every so often. So maybe in next presentation, BLM was already first citizen, right? First citizen on this. So what you get with this, you have predictable cost, no per token charges, and if you need to grow to CPU, same model, you add more replicas, and that's it. No retraining, and actually SLMify, it's built on improving or B2 version of the model as well. So the other thing, the benefit that you can get by running on CPUs is that you get for example, the benefits that you already have. For example, what I did is that I mounted the model and the data that I'm going to use using S3 so that I can have fault tolerant when the pod goes out or I need to scale out, I can start as fast as possible. We implemented something that is called Sochi, or it's basically parallel images. So unpack the image in different bits and start to download the different layers of the images in parallel. So instead of 60 seconds, you can get an image of the model, of actually your model as well, in less than 10 seconds. So what it's crucial here, I'm not gonna lie to you, when you run this CPU workload for real-time inference, you can get up to 30, 40, even a minute of end-to-end latency. But what matters here is the time to first token. So I'm gonna show you that if you optimize for this, for example, the router model can reply to you in 1 second, 2 seconds. and other models can reply to you in 30, 15 seconds, something like that. There are some things that I actually implemented. As soon as I got the first token, I start to stream the answer. So in reality, instead of course, end-to-end is going to take like 40 seconds. But as soon as you got your first token, you start streaming the answer, and it's meaningless, right? And there are other techniques that you can implement there as well. So finally, to see it here, how you can scale out. This is very important, and I think that actually it's very important to highlight that in any AI workload, you stop scaling based on CPU utilization. That is basically a saturation metric. That is a lagging indicator. Instead, what you will do is to, for example, start scaling based on queue depth. That you anticipate to what is going to happen, and that is a better approach. This works, again, for SLMs, for LLMs. It's the same pattern, and happy to go deeper into this as well. So I'm using Kera as well, or proposing to use Kera as well. You can configure scaling modifiers that allows you to create formulas so that you say, okay, if I'm getting, just by getting one queue request, I'm going to scale up and add 5 replicas instantly. And otherwise, just keep it a consistent scaling policy. But you can play around with this, right? So you can get new pods running very quickly by this. So to put it in a picture, how all of this ties together, you can basically have, in this case, I'm using Carpenter as well to launch the node, 24 seconds, downloaded the image, 9 seconds, warm up, 22 seconds, and you need to load the model into memory to start working. So around 55 seconds, you get your fresh node running, operative new model to start scaling out, right? So let me show you finally how this works on what I built, right? So this is basically what I built. And the reason that I'm showing you here is that you can see here, look at here, I'm showing you that it's basically CPU instances. These are not GPU instances. I have my orchestrator pod running here, and this is somewhat the architecture that I'm using, right? So if I put it in pictures here, this is basically what I built. The orchestrator GPU, CPU, for example, is running on CPUs, is calling then a small language model. If it's actually something relevant for the agent to start running, it's gonna run a RAG using OpenSearch here as well. It's gonna take the chunks of the documents to the auditor, and it's gonna able to produce the final answer, right? Else, it's gonna go and fall back to a LLM, right? So let me show you exactly this. And of course, this is I'm running this. Just basically, it's a live demo. Hopefully, the internet is not gonna give any problems right now, but it looks like it isn't. So in the same repository that I shared before, the demo that I built, that I'm showing you here today, you can actually run it and test it by yourself, and rely on the facts and not my words that actually it worked, right? So let's say, for example, that I have this question to my chatbot that is going to be a Kubernetes auto-scaling expert. And you can see here that what I'm doing here is pods are stuck in pending, but Carpenter is in launching new nodes. No errors in the Carpenter logs. It just says can launch more capacity. When I get the node pool, it says that we are 48 CPU use of the 50 limit. So Carpenter word permission. Should I worry about the limits or not? So if I paste that into my chatbot here, you can see here that it started to reply very quickly, right? So based on the improvements or the best practice that I showed you before, but you can see here that it was actually, if we pay close attention when it's finished, answering, it was basically the router answering here. I have high confidence that this is going to work. I'm going to go and do a call to the OpenSearch, to my knowledge-based system, and I'm going to retrieve 2 relevant documents from Carpenter official docs that I have, and I'm going to send it to the auditor SLM, and it's going to analyze the configuration. It's going to produce the result. So you can actually see here that the small language model actually corrects itself, and you can see the thinking process, right? So you can perfectly have a conversation or a very reliable system with an 8 billion parameters with reasoning, with a model with reasoning, with this. So let me paste a few other examples that I'm gonna show you. For example, I forward this to my manager. Can you take a look? So it's gonna go and say like, it's gonna say, okay, this is unknown confidence. I will be happy, however, I don't see any specific question in your message. And you can see here that it's actually calling an LLM here. And if I say like, hey, what is the weather like today in Seattle, right? Or in Bucharest. So if I say this over the chat here, and I run it here, but you can see how fast it starts to reply, right? This does not look like a Kubernetes autoscaling question. Now, let me show you one final question here that it's actually gonna show you that it's not all magic, and I'm not lying. It's gonna take a while to reply. So I send the question here. This is a fresh new question, and it's gonna take a while to respond back. Again, the SLM, the first router, was able to pick that answer very quickly. The knowledge, it took the knowledge base from very quickly as well, but it took a while to process the question from the bigger model. Still, it was not that bad, right? I do have some customers that are running this, and a funny story that I have with this is that they were running batch inference, meaning that they were recording the videos during the day. At the end of the day, they were processing the videos, and they were running on GPUs, and they got the answer almost immediately. It didn't matter because their customers were checking the information the next day. So they were actually overpaying for GPUs when actually CPUs were able to deliver what they wanted. So this basically tells, basically reinforces my point of you might not need GPUs, depending on your SLAs and SLOs. You might need to consider CPUs as well. So what this means for you, you have an SLM opportunity if you're calling an LLM2, route request to the right handler, validate configs before applying them, classifying documents, check responses before returning them to users. Again, you might have an LLM replying, but you might want to check or do a fact checking, and that can perfectly run on CPUs as well. So my action points for you are, or call to action are identify the repetitive decision in your pipeline, fine-tune an SLM, feel free to use the project that I shared before. It's a architecture reference. You don't have to use it, but you can actually get started and start to see if it makes sense or not. Deploy on CPU, keep the LLM for the complex cases, right? So specialization, bit sizes, the infrastructure is ready. What are you gonna build now? So these are the links to learn more, and I actually happen to wrote a book of Kubernetes autoscaling. So if you don't want to deploy the chatbot that I deployed, but you want to actually learn something and memorize it, happy to give you the one copy of the book if you just come and reach out to me, and that's it. Thank you very much.